It's 6:30. It's 6:30, and since Tim's not here, I guess I get to call the meeting to order. Do we have anybody out there that is new, not a member? Anybody?
Anybody out there?
Is there anybody out there? Yep. Okay, well, all the ones in the room here are members and we all know each other. So that was about it. If we don't have any guests tonight. Okay. All right, well, I guess I can introduce Patricia. Get started. Do it a little early. Patricia Bolan is an astrophysics PhD candidate at UC Davis. She's studying some of the first galaxies that formed in the universe. She grew up in Wisconsin and did her undergraduate work at Boston College and completed her senior honors thesis at Harvard and Smithsonian Center for Astrophysics. When she's not analyzing data, she loves doing anything outdoors, trail running, backpacking, rock climbing, snowboarding, and so forth. She's also passionate about public outreach and runs the Davis chapter of Astronomy on Tap. I won't think I would like to go up and check this out. A monthly event with public astronomy talks, news, and trivia at a local brewery. That sounds fun. Patricia is joining us from Lake Tahoe, so she's enjoying the mountain air as we speak. Patricia, I'm handing it over to you. Thanks for joining us.
Thank you so much. Thank you. And yeah, our next Astronomy on Tap is May 24th at 7 at Sunwork. So I'll give you the info if you want to check it out. All right, I'm going to share my screen here. All right. Let's make sure it's working. Sweet. Can you guys see that okay?
Yeah, we can.
Yep.
We have it.
Awesome. Okay. Well, yeah, just feel free to interrupt throughout. Yeah, I'll keep it pretty casual. I'll try and explain all the jargon or any terms I'm using before I use them. But if anything's unclear, just like interrupt me. It's totally fine. I'll go over what it means. Okay, so yeah, I'm just going to be talking about the work I've been doing over the last 5 years. I'm going to be finishing up towards the end of this year for my dissertation. So essentially what I'm looking at is some of the first galaxies that formed in the universe. It's a really cool era that there's a lot of mystery still about. So a lot of different scientists or astronomers are studying this period of cosmic history to try and figure out exactly what happened, get an idea of how galaxies evolved into things like the Milky Way and Andromeda, these big, beautiful spiral galaxies that we see in the present day. So yeah, I'll go a little bit into that and talk about my research with you guys. So I know you just gave an introduction, but just about me again. So PhD candidate at UC Davis, our department is physics and astronomy both together. So I'm on the astronomy side of that. Technically, the PhD will be in physics. But yeah, we have 5 floors in our physics building. 5th floor is astronomy. So we're all super tight knit up there. About maybe 1/5 to 1/4 of the department, faculty and graduate students and undergrads in the physics department does astronomy, and it's getting bigger every year. So we just started hiring astronomers like within the last 10 years, I think. And last year we officially made the name change from physics department to physics and astronomy. So it's getting a lot bigger at Davis. I think a lot more people are getting excited about astronomy, especially with all the new observatories and data that's been coming out. As was said in the intro, I love anything outside. That's why I moved to Tahoe last fall. I live in a van, so it's very easy for me to move around. Like I'm TAing, teaching assistant, a class in Davis this quarter, so I have to be there every other Monday. But it's, yeah, I love it. I just can't get enough of being outside. I usually work out here on this beach when I need to get work done in Tahoe. Yep, and then I love astronomy ever since my sister and I both got really into it together when we were kids. We'd be home alone watching Discovery Channel all the time. I remember when we were 7, we were like, oh, we're going to get PhDs in physics and work on that. And we're both doing our PhDs in physics now. She's at University of Illinois. So it was nice that we had each other to push each other and keep going forward with that. And I'm really lucky that she's the smarter one and was able to help me with homework when I was doing my undergrad in physics. So, okay, let's get into the actual astronomy part of this. So everything that I talk about in this talk, we're going to be looking back in time to when the universe was just a little tiny baby. I always refer to the galaxies that I study as little baby galaxies because they didn't have that much time to form yet. So essentially, just a brief overview of cosmic history. The universe right now is almost 14 billion years old. The best estimates we have right now are about 13.8 billion years old, which is a huge amount. And everything that I look at is encompassed in this yellow box that just drew there from within the first billion years of the universe's existence. So essentially the universe was less than 10% of its current age at this time. And the really cool thing about astronomy and the fact that we have a speed limit in the universe, the speed of light, nothing can go faster than it. What that means is that by the time that the light from this early on the universe actually reaches us in our telescopes here on Earth, it took 13 billion years for it to get here. So we're actually seeing that light as it was 13 billion years ago. So the cool thing about looking really far away when it comes to space is that you're also looking back in time. So when I'm looking at these galaxies that were within the first billion years of the Big Bang, we're seeing the universe as it was within the first billion years of the Big Bang. So I just love that about astronomy, that you're actually basically able to time travel by looking at galaxies. So let me explain a little bit about this word right in the middle, reionization, and what that means. So essentially what we're looking at here is just a history of the universe timeline. So on the left-hand side, you have the Big Bang, cosmic background was created. We don't have to get into what that is. And then over here on the right side, the present day, that's where you have fully formed galaxies, and the bulk of the universe is mostly ionized. So what happened from about, we don't know exactly when the onset was, maybe like a couple 100 million years after the Big Bang, up to about 1 billion years after the Big Bang, was this big phase transition in the universe called reionization. So basically what you have is tiny little galaxies starting to form, and the space around those galaxies is filled up with hydrogen gas. We call that space the intergalactic medium, just like the medium space between galaxies. And in the very beginning of the universe, and what we call the dark ages that we see over here on the left, all of that hydrogen that filled up that space was neutral hydrogen. So what that means, just like a little chemistry background, the hydrogen atom is the simplest atom we have. All that it is one proton at the center in the nucleus surrounded by an electron, typically. That's a neutral hydrogen atom. But that hydrogen can become ionized. And when it's ionized, that means that the electron that's orbiting around the proton gets knocked off and it's freed from the proton. And in order for that process to happen, something energetic had to come in and hit that hydrogen electron and hit the hydrogen atom and knock the electron off. So it gives the electron enough energy to free itself from the atom, and then that hydrogen atom is ionized. So this happened as a bulk process across the whole universe, throughout the whole intergalactic medium, sometime within the first billion years of the Big Bang. So essentially, the facts that we know is that there's some energetic light source that was emitting all of this high energy photons, high energy light, and it was knocking into all these hydrogen atoms, so that by 1 billion years after the Big Bang, all of that hydrogen within the intergalactic medium is ionized. So you just have free protons there, just the nucleus on its own, and all these free electrons buzzing around. So that's what we mean by reionization. It's this period of cosmic history where all of the hydrogen in the intergalactic medium went from being neutral, or electrons bonded to protons, to being ionized. So the electrons are freed from the protons. So the things that we know about this period of time is we know about when it ended, which is about 1 billion years after the Big Bang. And that's about it, pretty much. So there's still big questions surrounding this era. And that's what I was mostly focusing on with my thesis, is trying to figure out a couple of, kind of nail down some specifics of reionization. Okay, so the two big questions that I'm doing for this project, first, how did reionization progress? So like I said, really the only kind of fact that we have about reionization is we know when it ended. It's unclear when it started, how quickly it happened, what the actual sources were that were emitting all of this light that caused this massive phase change in the universe. So the first project that I did, I'll show the results from this in a bit, we're figuring out, kind of looking at a detailed timeline of how quickly reionization happened. We know that it could have taken a whole billion years, or could have happened really quickly, like maybe in one really fell swoop in 50 million years or so, which in cosmic time is a really short amount of time. Maybe it happened really rapidly and like all at once. So I compared some different samples of galaxies to kind of figure out what the timeline may have looked like. And then the last project I'm finishing up now is looking at the physical properties of these first galaxies. So how these first galaxies tie into reionization is that over the last 10 to 20 years, past couple of decades, there have been a ton more observations of these first galaxies as we've gotten better and better telescopes, able to look further back in time and see fainter things, have bigger mirrors and stuff. And the data that we found is that it's most likely that these young, faint, like first forming galaxies were likely key drivers to reionization. They were the ones emitting a lot of these photons that ionize the hydrogen. And one of the big questions now is trying to kind of get a profile on what the drivers of reionization looked like, to try and figure out what the population of galaxies was like at that time and how they actually caused all of the hydrogen in the universe to ionize. So those are the two main things that I'm looking at with my work. So before we get into how I've actually been doing this, I'm going to give you a lowdown on how all of the science is basically done. So galaxy, right, is just a collection of stars and gas and dark matter, all gravitationally bound to one another. Galaxies can look very different. They can have a wide range of masses, of brightnesses or luminosities, lots of different factors, different metallicities, which is just the elemental abundances in these galaxies. So if they have carbon or oxygen or helium or all these different, and fun fact you guys might know about astronomers is that we call everything that's not hydrogen and helium a metal. So like carbon's a metal, oxygen's a metal, nitrogen's a metal, which really annoys chemists. But yeah, in astronomy, anything that's not hydrogen and helium is called a metal, which is kind of funny. So yeah, which galaxies can we detect? How can we actually get data on these to figure out how they maybe contributed to reionization, how it happened? So let's just say you have a sample of all these galaxies. Something that has been studied a lot over the last 50 years since we've been observing galaxies is that there are way more faint galaxies at any given point in cosmic time than there are bright ones. So this might be a typical distribution of galaxies where you have a few bright galaxies here. The brighter ones are usually more massive. And then there's a lot more numerous, like about 10 or 100 times more of these really faint galaxies. But if you just take a picture of this blank sky and you're trying to get, let's say, a sample of galaxies and see what it looks like, those faint ones you're not gonna see them unless you have a really, really long exposure time. And basically you're gonna get sort of a biased view if you're just looking for galaxies by taking an image, or we call this a field survey, just looking at a blank piece of sky, taking a picture. You'll be limited by your exposure time, even for using something like Hubble or James Webb Space Telescope. It won't be able to detect those super, super ultra faint galaxies. But those are the ones that I'm super interested in, and that a lot of people who study reionization are interested in, because most of the galaxies in this era are these really, really faint ones. And we think that they are probably the key drivers for reionization just because they exist in such high numbers compared to the bright galaxies. So if we're only studying the bright galaxies that we can see easily, we might not be getting the full picture. So luckily, nature gives us a magnifying glass that kind of fixes this problem for us in some ways. So not sure some of you guys have heard of gravitational lensing. Basically what it is, it's a tool that helps us to find these really, really faint galaxies without having to spend 30 hours straight on a space telescope in order to detect them. So physically what's happening here is you have a really large galaxy cluster. So gravitationally bound multiple different galaxies, we call that a galaxy cluster, and that's in the foreground. So if we're here on Earth, it's essentially right next to us in terms of space-time. But what it does is that it has all this really kind of complicated distribution of mass and especially dark matter. And light from behind those galaxies gets distorted as it passes through our view, as the light from those distant galaxies gets bent around the cluster. And the key thing that helps us out here is that as that light gets distorted, it also gets magnified in a lot of senses. So as you can see in this picture here, if you follow my mouse, I hope you guys can see the mouse. We have these beautiful arcs. These are called lensing arcs. There's a lot of good ones in this photo here. This is one of the new James Webb photos. But yeah, it creates these like beautiful arc effects. Sometimes there's even what's called Einstein rings. We get like the lens just matches up perfectly with a background source. So you get like a perfect circular ring around it. So gravitational lensing is a tool that is super helpful for us because it takes those intrinsically faint galaxies and it magnifies that light so that we can actually see what these faint galaxies look like, determine physical properties of them, maybe get emission lines or see what kind of metals are present in them, without having to spend dozens and dozens of hours on a telescope looking at them. So yeah, this is what I've been using basically for my whole thesis. All the galaxies that I look at are behind magnifying clusters. So since I'm probing those really intrinsically faint, super common galaxies during ionization, we basically need to use this nature's magnifying glass in order to actually see them. All right, so now we know that we're looking for faint galaxies. We're trying to see how these faint galaxies contribute to ionization, how they shaped the universe within the first billion years of the Big Bang. So now we know how to detect them. We're going to use these gravitational lensing clusters that just happen to magically magnify the light of the galaxies that we need so that we can actually see them. But when we say that we're actually detecting or seeing these galaxies, what does that actually mean? So in astronomy, there are basically two different types of data you can get from a telescope. Some variations of this exist. The first one is what you might be most familiar with, photometry or images. So on some level, a telescope is just a giant camera, right? You're just taking a lens, getting all this light into a collecting mirror, and then that mirror focuses all the light on the detector there, just like a camera. So the most common, probably most popular form of studying galaxies or studying anything in astronomy is using photometry. As you can see here, this is one of the new James Webb images that came out last year. You can detect a lot of different galaxies. You can see a lot of the beautiful like lensing arcs in this one too, all these little squiggly guys here. Those are galaxies that the geometry lined up such that the lensing cluster bent that into a perfect little arc around there. It's really cool and you get to see that. So yeah, this is the first thing that we do when we're looking for galaxies. We just take a picture of that lensing cluster. And then I'll get into a little bit how we determine how far away those galaxies actually are. The thing that I actually do though, the kind of data that I collect is spectroscopy. So this is where, like if you see the Pink Floyd Dark Side of the Moon album cover, right? You put a prism or a grating up to a light source, that's white light or any kind of integrated light over multiple different wavelengths. It'll take that light and spread it out over all of its wavelengths. So like in this graph here, this is a James Webb, again, spectrum. And you'll see on the x-axis here, this one going horizontally, the wavelength of light. So basically at every single wavelength, you have a brightness. So this one's looking at amount of light blocked because we're looking at exoplanets, which is a totally different thing. But the basic idea is the same with galaxies. At every single wavelength, you have an amount of light that you get from it. And spectroscopy, while it doesn't produce the beautiful pictures that we get from photometry, I think is way more important in terms of actually understanding galactic physics. My advisor always says, she's like, a picture is worth 1,000 words, but a spectrum is worth 1,000 pictures. Because for every single point here, you can see exactly how much light it's emitting. And that tells you a lot of different things because different types of stars, different ages of stars will emit light at very different wavelengths or different energy levels. So if you know exactly how much light is being emitted at a given energy level, you can tell a lot about what that galaxy is actually made of. So the thing that I study most is spectroscopy. I get spectra of these galaxies. And it gives us a ton of information about what they're actually made of and what they look like. Okay, so now we know we are looking for faint galaxies, trying to see their contributory ionization. We're detecting them using photometry and spectroscopy. But then once we get all this data on the telescope, how do we know how far away is it? Because the whole point of everything that I'm studying is that we're looking at galaxies within the first billion years of the Big Bang. So we have to be pretty sure that they actually are where we think that they are, right? Based on the data that we have. So you guys are probably familiar with the Doppler shift, at least in terms of sound. So when a siren goes by you, right? Let's say an ambulance is driving by, if it's coming up from far away and coming towards you, the sound emitted by that siren will be shifted into a higher frequency, right? It'll go like, whoop. And then as the ambulance is driving away from you, it'll be the exact opposite. It'll go, whoop, and it'll shift it down to a lower frequency. So that same exact effect happens with light, and that helps us to figure out how far away galaxies are. So the cool thing about the universe is that it's always expanding in every single direction. So that means that every single thing is always moving away from everything else, except for things like galaxy mergers and where there's gravitational events. But in general, on the large scale of the universe, every single galaxy, the ones that I'm detecting, and everything but Andromeda, basically, because we're going to collide with Andromeda in however many billion years. But everything else is always moving away from each other. So I just think about it as like if you're baking a raisin bread, right? You have this little loaf here, you have your raisin spread out, and as that bread gets baked, everything, the whole dough itself, the dough is like the universe, expands outward, and all those raisins are further away from each other than where they started. So that's the same thing here. So then if we think about the Doppler effect in terms of this, that means that the galaxies, every galaxy that we're looking at is receding and going further away from us. That light that we see from the galaxy will get shifted into longer wavelengths, or red shifted. And that word just comes from the fact that blue light has a shorter wavelength than red light. So if something's moving towards you, it gets blue shifted. If something's moving away from you, then it gets red shifted. So we use this measure of how far that light is red shifted to figure out how far that galaxy is away from us. And the further the light is red shifted away, then the further that galaxy is away from us. So essentially, we're looking for galaxies that have very, very, very red shifted light. All right. So this is just a video that kind of shows how that process works. I'll explain what's going on first, and then play the video a couple of times. But this is essentially how we first figure out, so the steps to figure out how far away a galaxy is and which ones we actually want to study. So first, we get photometry on them in multiple different wavelength bands, right? So that's what this is showing here. All these things, these filters you see, F435, F606, all the way up to F160. So what these are, this is specific to the Hubble Space Telescope, but it works with any telescope with multiple different detection bands. So when you take an image with a telescope, Hubble is an optical. So these are all wavelengths that we could see with the naked eye. But you pick a specific wavelength range to see it in. And usually what you'll do is you'll take a picture of the same exact target in multiple different filters. So like the most basic easy one would be to do blue, green, and red, RGB. And then when you're reconstructing the picture of the galaxy, like those James Webb's ones I was showing earlier, you're stacking together the red and the blue and the green in order to make that beautiful image. But when you actually take a raw image on a telescope, you're only getting blue light if you're using a blue filter, or you're only getting the red light if you're using a red filter. So this comes in handy for trying to detect these galaxies using this break or drop off technique that this video will describe. So let's say we have, I believe there are 9 different Hubble filters in this video. This Z value here, it's a Z equals 3.35. That's just redshift, and that's a measure of how far away something is. So basically, the higher that number is, the further away that galaxy is. Just for context, that number I've been using a lot, billion years after the Big Bang, that corresponds to redshift equals 6. So the redshifts of galaxies that I'm looking at between like 500 million years to a billion years after the Big Bang lie between about redshift 6 and 11. So let me play this here. So essentially this gray box down here shows the intrinsic spectrum of a galaxy, right? So all of its light has different wavelengths spread apart. So as a galaxy gets further and further away, right? Yep, that's galaxy redshift. And these little boxes down here correspond to the images of that galaxy in those different 9 filters. So look, as we redshift this galaxy, okay, yep, looks like that. Further and further away, right? I'm going to pause it here just to take a look at this. So if this galaxy that we're looking at is at redshift 7.35, let's look at the images down here at the bottom. We won't detect that galaxy in any of these 5 bluest filters to the left. We'll only detect the galaxies in the redmost filter because the spectrum of the galaxy is this characteristic break right here. And I won't get into where that actually comes from. I'm happy to talk about later. But essentially, this break helps us to determine where these galaxies actually are. So as the galaxy gets more and more redshifted, it'll only show up in the redmost filters of the Hubble Space Telescope. And it's even more helpful to have, we have another space telescope that we use for a lot of our data called Spitzer, which has been decommissioned about 2 years ago. But JWST is essentially in the same wavelengths as Spitzer. It looks at infrared wavelengths, so even redder than all these Hubble ones. And that helps us to find even higher redshift galaxies than here. So essentially, that's the process we use. Is the first thing we do is we take images and we do photometry in all these different Hubble bands, as well as Spitzer, even further to the red wavelengths. And we look for these dropout galaxies. So we compare the images and all the different filters. And if there's a galaxy that only shows up in those redmost filters, then we're pretty sure that that's going to be in our high redshift, or these first galaxies range that we're looking for. All right, so when I got to Davis, all this work was already done. The grad students before me did all the photometry and already found the dropout candidate galaxies that we're looking at. So that's the first step. The next thing, though, is what I've been talking about is the best thing ever, spectroscopy. That's what I do. It's the most reliable redshift, or measure of redshift. So when you're doing that method with just photometry, there are a lot of uncertainties in there. I mentioned that characteristic break where all the light, blue red of it, you won't see. There's another break that mimics that it could be an actual lower redshift galaxy that we're mixing it up with. So the only way to for sure know the redshift of the galaxy, or how far away it is to get a spectrum on it and to detect an emission line. So this here, you see Lyman alpha, the one that I'm showing out with my cursor, that's that characteristic break that we talked about. See how the flux or the light just kind of drops off as you go blueward of that. That's because all those photons get absorbed essentially by the galaxy before it exits. So if you can find this Lyman alpha line, which is what I'm looking for in my spectroscopy, or any of these other examples of different emission lines. So these are just emitted by different chemicals or metals that are within that galaxy. They emit light at these characteristic wavelengths. And that tells you exactly what the galaxy is composed of. So this is an example of a spectrum from JWST, from the James Webb Space Telescope. Internet for a bit. Okay, you guys see me?
Patty, yes, we can hear you.
Are we back? Okay, sorry about that. Yeah, let me share again. Sorry about that. The internet went out for a bit. Okay, so this is where we're at, looking at the spectrum of this galaxy. So yeah, essentially the best way to figure out how far away a galaxy is to get a good spectrum on it and to see at least one of these chemicals in an emission line, because we know intrinsically at which wavelength that chemical is being emitted. So however far redshifted that we actually see the emission line, there's a really easy formula that tells us how far away that galaxy is or what redshift it's at. Okay, so this is where my work started. Basically, when I came into the program, we already had all the photometry data. We had all the dropout candidates, the galaxies that we wanted to follow up with spectroscopy. And then a lot of the work that I did was collecting data using Keck Observatory in Hawaii, which is on Mauna Kea. So it's always fun doing observing one. You have to do a lot of prep for it, like design all the masks, because essentially you don't just point this the spectrograph right at the sky. You only allow it to let light in at very little slits where you expect your galaxies to be. So a lot of the work is before the actual observing, designing those masks so that we only let light in and only see the galaxies we want, don't have any contamination from bright sources. And we have this is in our remote observing room in Davis. So we can control the telescope from our physics building, which is really cool. We don't have to go to Hawaii. It is nice though when we do get to go. That's the cool thing about doing astronomy is your work trips are usually to like Chile or Hawaii, or the Canary Islands or whatever all these big telescopes are. And I was able to go last year on one of my trips to Hawaii. This is at the top of Mauna Kea on the Big Island. You can drive up to the top. I ran up to the top. Got a lot of altitude sickness once I got up there. But yeah, it was really cool to run up and like actually see the telescopes in person that I'm getting like all of my data from. So that was super rad. I was stoked to finally get up there and see them in person. But yeah, so Keck Observatory is the one that I'm using basically to collect all of my data. I've spent over like 25 nights on the telescope in the past 5 years. How it works is you apply for time. So my advisor applies for time. But then it's the grad students who actually run all of the observations. So yeah, that's been a lot of fun to stay up all night and work on that stuff. And it's really exciting to actually see the data in real time and see if you actually see any emission lines right away. So what I'm left with in the end, so we talked about how to detect galaxies, the different types of data we get, why we want to look at faint galaxies. So the sample that I'm using for my whole thesis is almost 300 galaxies with both imaging or photometry and follow-up spectroscopy from within the first billion years of the Big Bang. So this is the sample that I'm using to answer those big questions that I introduced in the beginning. It's the connecting thread kind of my whole dissertation, because the two projects I'm working on are pretty different in terms of analysis. But the sample is kind of what brings all together. So this is one of the biggest, like characteristically faint samples of galaxies at these high redshifts that we have. Even with JWST, it's going to take a lot of time to get as many galaxies as this. With as deep spectroscopy as we have. So I always just like to show this as a comparison. So when you think of galaxies, you might think of these beautiful spiral. This is, I think, the Whirlpool galaxy or something from JWST. But what my galaxies actually look like are this. They're just tiny little like pixelated blobs that you can barely see. And this is even with the magnification effect of gravitational lensing. This is about as bright as we get. So it's hard to get good data on these galaxies. For a lot of them, we're spending all night on the same field. So we're looking basically 10 hours straight just to try and get any little blip of light or to see any little emission line from these galaxies. And a lot of times it doesn't work out, but we still get valuable data from them, even if we don't see a real emission line. So yeah, we're looking at these tiny little baby blobby galaxies, much smaller than the Milky Way is. But it's really cool because we're looking back in time 13 billion years to actually see them. So going back to the big questions, how am I using this sample to actually answer what's going on here? So the first one I brought up, how did reionization progress? So the timeline of that reionization transition is still pretty unclear. So I use this sample of galaxies to try and figure out how quickly the universe ionized. So essentially, this is just another kind of history of the universe type of plot. So on the left here, we have neutral hydrogen, what we call the dark ages, just because light can't escape through neutral hydrogen, it all gets absorbed up. So that's why they called it the cosmic dark ages. And then over on the right here, present day, you have all these big, beautiful spiral galaxies. So essentially at redshift 6, or billion years after the Big Bang, we know that this this XHI down here, that's the neutral hydrogen fraction. So just the percentage of hydrogen that's neutral versus ionized. So when we say neutral hydrogen fraction is 0, that means all of the hydrogen is already ionized. So that happens at around redshift 6 or billion years after the Big Bang. We know that's neutral. We know that way back in the very beginning of the universe, like first 100, 200 million years, that neutral hydrogen fraction was 1. So all of the hydrogen was in a neutral state. But it's a big question mark what happened in between. So the basic premise for how I kind of deduce sort of a timeline at two different redshifts during reionization was taking a sample of galaxies that spans from redshift 5, so a little bit after reionization, all the way up to about redshift 9. And we split them into different bins and we looked at how much light that each of them were emitting. And the key about this whole process is that they were all intrinsically had the same properties. They were all about the same mass and about the same brightness. And dustiness, which is another thing we can measure in galaxies. So we know that intrinsically they should have been emitting about the same light, but what we found was that these galaxies at much higher redshifts were emitting way, way less light. So what we did was we did sort of this complicated statistical process comparing to models of reionization to figure out how ionized the universe was at each of those redshift bins. So this is, I'll explain what all this is. It looks complicated, but it's not too bad. This is kind of the end result of my last paper I published in 2022, kind of looking at this process. So the orange stars are our points here. What we're looking on the x-axis is kind of flipped from what we saw last time. So higher redshift over redshift 10 is over here on the right-hand side. Redshift 6, or when reionization was complete, is over here on the left-hand side. And that neutral fraction I was talking about is on the y-axis. So you can see at redshift 6, we're down to 0 neutral fraction, meaning all the hydrogen is ionized. And then up that around redshift 10 here is where we get up to a neutral fraction of 1. So these orange points here are the ones that we determined in this paper last year. And the key result from this whole process was that we found that reionization happened pretty quickly. So at this redshift of 7.6, that's where one of our bins was centered of galaxies that we looked at. We found that the universe was still mostly neutral. So we had an 83% neutral fraction at redshift 7.6, or about, I think that's about 600 million years after the Big Bang. And then our second redshift bins is at redshift 6.7, and we found a huge drop in the neutral fraction between these redshifts. So the key here is that this, in cosmic history, was not a lot of time. So between redshift 7.6 and 6.7, we're talking about like 150 million years, which compared to the age of the universe now, 14 billion years old, that's a really, really small amount of time. So what we found is that this reionization process actually happened pretty late and pretty rapidly. So by the time the universe was about 600 million years old, it was still mostly neutral. And then within the next 150 million years after that, almost all of the hydrogen got ionized. So now that we kind of constrained this timeline, the next big question we had was, okay, given that, what are the properties of galaxies, what are the properties of whatever it was emitting all of this light that caused it to happen so quickly? So that's where we get into the second project that I'm still working on now. Hopefully we'll be done in the next month or so is the plan. What are the physical properties of first galaxies? So if we're going to kind of believe a lot of the studies that came out of the last 10 or 15 years or so, saying that these faint small galaxies are the ones emitting a lot of the ionizing photons causing reionization, we want to kind of get a detailed look into what those galaxies looked like, to kind of figure out how they emitted all of this light and how many of them there were. So what I'm doing now, I was working on just before this, is looking at physical properties of galaxies. Essentially, we have two different, in those, that sample of 300 galaxies I have, some of them we got that emission line from. If you remember me showing that spectrum before, where that characteristic break, where there's no light and then a lot of light, that's the line that we're looking for. It's called Lyman alpha emission. It's from hydrogen. We don't need to get into the details of it, but essentially, for some of those galaxies, we have that emission line from them. And there are studies that show that when a galaxy emits that line, it's likely one of the ones, it's correlated a lot with emitting ionizing photons. So if we detect that Lyman alpha line in galaxies, we're pretty sure that that's one of the galaxies that's contributing a lot to reionization. So we really want to study those galaxies a lot more to see what they look like. So what we did was we compared the sample of galaxies which have this emission line and those that we don't get the emission line from, no matter how long we looked at them for, to kind of see if there's any physical differences that give us clues to how those galaxies that emit that line had all of these ionizing photons that was emitting to ionize the universe. So the properties we're looking at for all 300 galaxies in the sample is stellar mass. So basically that's just like the mass of the galaxy. Most of the mass of a galaxy, excluding dark matter, is in stars. There's not as much in gas. So what we're actually measuring is stellar mass. The age of the galaxy, it's shown that the younger galaxy is, the more likely it is to be able to emit ionizing photons for a multitude of different reasons. The star formation rate, so galaxies are always, not always, but some galaxies are what we call quiescent, which means not forming stars anymore. But a lot of these galaxies from within the first billion years of the Big Bang are forming stars. So we can have a rate, basically you look at it in solar masses per year, or mass of the sun per year. And we're trying to see if star formation rate correlates with ionizing or emitting ionizing photons. UV beta slope, which just corresponds to dustiness. So beta slope tells you what kind of stars are in a galaxy and how dusty they are. So dust is something that astronomers are always annoyed by because it always gets in the way of stuff. It basically takes blue light and turns it into red light. With these galaxies, we don't have to worry about dust too much just because a lot of dust builds up over time. So within the first billion years of the Big Bang, it's not that much of an issue. But yeah, the dustiness of a galaxy can tell you a lot. It correlates with its age and how many ionizing photons it's emitting. The intrinsic brightness of a galaxy is correlated a lot with how much it can emit, right? If a galaxy is brighter, then it's probably going to be emitting a lot more ionizing photons. And another follow-up thing that I was doing with Keck Observatory last year was looking for the presence of ionized carbon. So it's called C3, doubly ionized carbon emission. I can answer more about that later if you want, but I decided not to go into the C3 hunt for this talk. But yeah, essentially you're looking for another emission line besides Lyman alpha in a lot of these galaxies. And if we didn't end up detecting it any, which is why I didn't go into it. But if we did find that carbon in one of those galaxies, that gives us a lot of insights into its physical properties and what it's actually made of. So yeah, I think that's pretty much it for my research. I did just very briefly want to touch on the fact that this is a really exciting time to be doing reionization and first galaxy science, just because of the launch of the James Webb Space Telescope. So one of the, I think there are 4 or 5 different like main science goals that JWST was launched with. And one of them was detecting first galaxies and pushing back to see how far away we can detect these galaxies and determine physical properties, what they're made of, what metals they have, how big they are, how bright they are, and things like that. So it's a really exciting time to be working in this field, just because every single day it seems like there's a new paper on this really distant galaxy being emitted. So these are just some from like the last like month or two. All these papers coming out of galaxies at higher and higher redshifts, meaning further and further away. So like putting out to redshift 16 is insane. That's like 150 million years after the Big Bang or something. So some of this stuff kind of challenges our ideas of galaxy formation in general, just because based on the models that we were using previously, you kind of wouldn't expect to find this massive of galaxies this soon after the Big Bang. So a lot of these new discoveries from JWST are kind of helping us shape maybe even a new model of galaxy evolution formation in the beginning of the universe. Yeah, so it's a really exciting time to be studying this. Yeah, I'm stoked to be doing it. And yeah, cool. I can't wait to kind of get results for this last project I've been working on and see if we can get a little more insight into drivers of reionization. So yeah, that's all that I had today. So thank you guys for listening. I'd love if you guys have any questions to talk about that.
Right. Thank you very much. We have questions. We have questions?
I'll kick it off with a question. Can you talk about how the Hubble volume influences your ability to see the first galaxies? My understanding is that you should have galaxies that are outside of the Hubble volume expanding faster than the speed of light. So I would sort of expect that all first galaxies should already be outside the Hubble volume and we can't really see them. Is that correct? And do you think
That's a really good question.
Okay.
Yeah. Yeah. So that gets into, yes, that's a really good question. And it's the answer is very nuanced because it goes into the fact that we are seeing the light as it was emitted from that galaxy when it was at that point, but now it will be actually further away beyond that Hubble co-moving volume. So because it's still moving away, like as we speak, that galaxy is getting further and further away, but the light that it emitted before it kind of moved out of our zone of being able to see it, we were able to still track that light, if that sort of makes sense.
It does. I get it.
Okay. Yeah, but that's a really good point. Yeah, because now if we try to detect that galaxy now, then it'd be out of our, but since it was emitting that light, however many like billion years ago, we're able to track that light to where it was then, even though the galaxy's out of our field of view now.
Okay, I get it now. Anybody else have any questions?
Yeah, I do.
Go ahead.
How many galaxies are there in the
Oh.
universe?
That's
lot.
a great question.
Yeah,
That's honestly a really good one because we don't know. Definitely at least trillions, right? At least probably hundreds of trillions. But that goes into what I was talking about at the beginning, where there could be there are some galaxies that are only made up of about 100 stars, which, to give you context, the Milky Way has a mass of about 10 to the 10th solar masses. And we're
Yeah.
talking about galaxies that have 10 to the 2 solar masses.
Oh,
So those are, which like would be impossible to detect anywhere outside of our own like local universe, like basically right next to the Milky Way, because they're so faint.
yeah.
So the further away that it gets, the fainter that light gets to us, right? Because it's being spread out. So yeah, we actually don't know how far down basically in mass bins that galaxies go, at least at really high redshifts, at really far away, because we can only detect them by lensing, and even then we're only detecting down to about like 10 to the 6th or 10 to the 7th solar masses, just
Yeah.
a range of sizes. So there could be galaxies even fainter than that, that even with lensing, they're too faint for us to detect. So yeah, definitely at least hundreds of trillions, but yeah, there could be way more that we just have no way of detecting.
Okay.
Question. So are you finding that the earliest galaxies are full of very massive stars, and are they even older galaxies?
Yeah, that's a really good question too. Yeah. So yeah, the light that we see from a galaxy, right, is just a combination of all the light from the individual stars in that galaxy. So what we find with these really far away young galaxies during reionization is that they're mostly filled with blue light, and blue light means young, hot, big stars. So essentially, yeah, stars, when they're first forming galaxies, especially way back during reionization, there weren't a lot of metals or any other elements besides hydrogen, helium, and like trace amounts of lithium, because those metals build up over time as stars explode and die, right? That's how we get bigger and bigger elements. So with these galaxies that we're looking at, the stars in them have to necessarily be typically much bigger than in galaxies that we see today, because they're only made up of hydrogen and helium. Mostly there's some other, like at this point there's probably some carbon and oxygen, but it's primarily hydrogen and helium, the simplest elements, and those ones tend to take a lot of energy in order to fuse together. So what that means is that those stars have to be a lot bigger than like even the sun, let's say. But yeah, those stars, the hotter and bigger a star is, the more short-lived it is too, because it'll burn through all of its fuel through fusion a lot faster. So we're usually catching these galaxies with these stars kind of at the key moment before they've already blown up and gone supernova. But yeah, we find that these young galaxies tend to be made of bigger, bluer, brighter stars than galaxies we see today.
They're burning hydrogen, hitting CNO process a lot faster. Your medium-sized stars, which would cause the ionization, because they were giving off so much ultraviolet, would cause the ionization to happen quicker. Is that what we're assuming?
I think so. Yeah. That's a really good point. Yeah, I think that comes into it. Because reionization just comes to how many UV photons. UV is the wavelength of light, or general range of wavelengths of light, that we need in order to ionize that hydrogen. It needs to be at least 1216 angstroms is the magic number, or shorter wavelength. So yeah, those stars that are going through those CNO cycles faster and emitting a lot more ionizing photons maybe could have been the ones responsible for such a rapid reionization that we found. If a lot of those galaxies are all forming at once during reionization and they're all emitting this light at once, then that could be responsible for how that happens.
So how early are we finding carbon?
That's a great question. So
redshift?
they did find carbon-3 at in the redshift 11 galaxy, that one like beautiful spectrum I showed. They found that line that I'm looking for, C3. I think that's the furthest away see 3 so far, except I'm sure that JWST will find an even further one any day now. But yeah, the fact that we have ionized carbon at redshift 11, that's I think about 400 million years after the Big Bang. So that means that there were galaxies before that, right? Or at least some kind of star cycles before that happened that created the conditions where carbon could be made.
We
Okay.
also, earliest galaxies would not really have these spirals, that they would just be massive, I mean.
They're just little blobs. Yeah. I think it takes about, I don't know the shortest amount, but a lot of the galaxies that we see today, like the Milky Way is 10 billion years old. So it usually takes on the order of about 10 billion years for it to form that spiral shape, because galaxies form mass as they get older. They usually get bigger and brighter as they go along. Typically, there's a lot of nuances to that. But yeah, it's usually on the order of probably about 8 to 10 billion years in order to form that spiral shape.
Okay, what is the biggest galaxy?
That's a great question. I'm trying to think. So I know the Milky Way is about like 10 to the 10th solar masses. I think Andromeda is a little bigger than that. Our neighboring nearest galaxy you can see in the night sky. I think that's about 10 to the 11th. But I'm not sure what the most mass. That's a really good question. I think they typically go up to about that with like 10 to 11, 10 to the 12th. So that's about 100 times more massive than our Milky Way is, which is huge. Like the Milky Way is relatively very huge.
Yeah. Yeah.
But yeah.
Okay, thank you.
Yeah.
You hear me from this?
Okay, yeah. Can you hear me now?
Yes.
Okay, you mentioned earlier that there were some galaxies with 100 stars. I've never heard of such a thing. Can you?
Yeah. So yeah. Well, on the order about like a few hundred stars, which is crazy. So like basically any galaxy that's 10 to the 7th or less solar masses, we call that a dwarf galaxy. So we have a lot of dwarf galaxies circling around the Milky Way, but that's how they found these. So basically the definition of a galaxy, let's get into that first, how we actually, like, how do you call a gravitational collection of like 400 stars a galaxy? The key thing is that it's in what's called a dark matter halo. So essentially it has, and we still don't know what dark matter is, but we can detect it gravitationally. Like we know that it's there based on the light that we see coming around it. So that's how they determined that these things were galaxies. They were found in our local region. So like basically right outside, like orbiting our galaxy. And they were collections of about like, I think 400 stars within their own dark matter halo, which is like the key thing that defines a galaxy, is that it's within its own dark matter halo, or basically just a gravitational well of dark matter that everything kind of resides in. Is kind of the best definition I have for dark matter halo. But yeah, it's crazy. I think, yeah, the only ones that we've been able to detect so far have been like right outside the Milky Way, basically within our own local group. Yeah, so we don't know how common those things are, because they're basically impossible to detect any further away, at least with the instruments we have now, because they're so faint. So if the further you get away, the harder it is to see, and they're already like super faint because they're so small. Yeah.
Yeah, I never thought of that. I think it seems like there's going to be a trap one of these days where you find out dark matter isn't what you thought it was. Oh, darn, we could find galaxies around something that's got nothing to do with nothing.
Yeah, right. I know. Yeah, that's why I'm not doing dark matter. It's like I can't deal with the disappointment if it's all fake.
Hope not.
I have a question. How do you pick your targets?
Yeah, that's an awesome question. So yeah, essentially it starts with that process of somebody way back when in like the 90s, I think is when at least the sample that I'm working on got started on. They found these lensing clusters, usually found, so like if you guys have heard of the Hubble ultra deep fields, essentially the director of Hubble, I forget what, sometime in the 90s, just decided to take like his own time on the telescope. He's like, I'm just going to look right here for really long for like days at a time. And he found all these tiny little galaxies in there, which is so insane. But anyway, that kind of got me off track. But I think so essentially Hubble found these lensing clusters, which you can tell what the lensing clusters are because in their images, they'll have those arcs there. So they essentially found really massive galaxy clusters nearby us, took images of them. And in those images, we see the distorted light from background galaxies, which is the ones that I'm looking at. So essentially the first step in knowing which one's to target, we have all these images from Hubble of these galaxy clusters. And then for each of the galaxies in that field, especially the reddest ones, which are more likely to be the high redshift ones that we're looking at, you take essentially that process that I described a little bit earlier. So you take images in multiple different filters on Hubble, and then you look for those dropout galaxies. So you look for the ones that only show up in the reddest filters. And that gives you kind of idea of what weight or what redshift that galaxy might be at. And then from those, that's how we figure out which ones to target. Is we pick the galaxies from those Hubble images of the cluster, the lensing cluster fields. We look for the ones that are dropped out, so galaxies that only show up in the reddest filters and not in the blue ones. And then those ones we put on our slit mask when we're doing spectroscopy, and we try and get spectra of them to actually confirm where they at with an emission line, essentially.
Thank you.
Thank you.
Mhm.
I have another question.
Yeah.
Getting back to the galaxies that show up with the lensing, showing up as arcs. Why are they arcs? Why are they arcs, not a complete ring?
Yeah, so it all has to do with the geometry of basically how the mass is distributed in your lensing cluster, right? So that's a big process. That's a step that I like totally left out of this whole thing because that was all done before I got to the program too by previous colleagues. But yeah, once you take a picture of this map, which you have to do in order to figure out, because it's like we know that some galaxies behind are being magnified, but we have to know how much the light is being magnified by if we want to recover intrinsic qualities of that galaxy, right? So in order to figure out how much everything is magnified by, people create what's called lens models and magnification maps. And I wish I had a picture I could show you guys. It looks really complicated. So you have something right in the middle called the brightest cluster galaxy. It's just basically the center of the galaxy cluster. And then around it, they use basically multiple images because a lot of times with lensing, you'll get a background galaxy that shows up 3 or 5, it's always an odd number, which is interesting, different times in that same image. So they use those multiple images and they use galaxies that have spectra of that they know exactly how far away they are of, so they know how much they're magnified. And they create what's called these lensing maps. I've never done this myself, but I use the results of the lensing maps. So basically that tells you how the matter is distributed in this lensing cluster. So if you get what's called critical curves, essentially. So you have your brightest cluster galaxy, these kind of weird curves all around it. And if one of your background galaxies happens to land right on a critical curve, that's where you get an arc. And if it's like slightly off the critical curve, and if it lands right dead center on the critical curve, that's where you get an Einstein ring, where it's just a whole circle of light around it. So it really just depends where that galaxy lands on the lensing field itself of the galaxy.
Oh, can I be heard? Hi, Patricia.
Is it
Hi.
on?
Yeah, I can hear you.
Excellent talk, by the way. Enjoyed
Thank
every
you.
minute of it.
Oh, good.
I've read recently about some galaxies being, having such a large redshift that it's causing people to have to, rethink the initial conditions under which galaxies and stars first formed, near the end of the dark era.
Yeah.
Do you have anything you can elaborate on that?
So I think we actually talked about this at our last Astronomy on Tap because it was causing a lot of hubbub in the astronomy community. So remember I said earlier how there are 2 different ways to determine how far away a galaxy is. So first you do photometry, and that gives you an estimate of how far away it is. Then you follow up spectroscopy, and the only sure way of knowing the redshift of a galaxy is by getting a spectrum on it and identifying an emission line and seeing how much it's redshifted. So those
Mhm.
galaxies in those papers where they made those claims only had photometry so far. They weren't able to, so they've since gotten the follow-up spectroscopy. And one of them was published, I think 2 weeks ago. And basically the main galaxy in that paper that they were using, they said it could either be at redshift 5 or 17. So 5 being like 1.1 billion years after the Big Bang, or like 100 million years, like right after the Big Bang, basically. And after they got the spectrum of it, they found that it was at redshift 5. So it wasn't actually as far away as they were hypothesizing. But I think a lot of journals kind of ran with the sensationalism of it and we're like, oh, well, if it is this far away, then that changes everything. But that one galaxy they found was not at redshift 17, which if it was, and it had the mass that they found that it had, then we have had to rethink a lot of galaxy formation models. But with the follow-up spectroscopy, which is, like I said, I think is the most important part of astronomy, they did determine that it wasn't at redshift 17, it was at redshift 5. So that one wasn't 100% true, but yeah. Huh?
Any other questions? Anybody in Zoom land there? Okay.
All right.
Once again, Patty, thank you very, very much.
Thank you guys.
Thank you.
Yeah. Thanks so much for listening, y'all. It's nice to talk to you. Yeah.
Please contact us again. Have you speak to us again when you get through with some more stuff. Or
Yeah, that'd be
you're-
awesome.
please, if they're willing to give us a talk, please have them contact us. We're always looking for speakers.
For
Yes.
sure. Yeah, I will.
Definitely.
All right. Well, thank you guys so much. I'll see ya.
Mm.
I'll email you the info
Okay.
about astronomy on tap in Davis if anyone wants to go in a couple weeks. All
Okay.
right. Bye, guys.
Bye-bye.
All right,
All right, let me bring up the
agenda.
announcements.
Announcements, yes, true. All right, so.
Let me share it for a second now.
All right.
Please stand by.
Me too.
Can you guys in Zoom there see the announcements?
See it. Yeah,
You see the announcement slide?
yeah.
Okay.
So this Saturday, we have 8 p.m. Jeff? Yep. Okay. The Baldwins are on it. And then we have Highway 4 Star Party. On May 17, we have a lunar occultation of Jupiter. So we get it at 4:42 a.m. with Jupiter already in occultation. So if anyone wants to get up and do that, take pictures, please. May 20 is the high altitude, probably heliport, because I'm sure there's still going to be snow up at Feather.
It's got pictures of 30 minutes downhill from Butler.
Yeah.
There's still 10 feet of snow.
Oh, boy.
So everybody, Jeff is going to rent a snow cat.
Yeah.
Up to River Hill. We'll be meeting back here on June 8th. Oh, wait a minute, public outreach first. May 26th is not going to be sky tours. So Yatsik, the Kostroiko, the astronomy teacher at Delta, we're just going to do it while Delta is having classes. So
Yeah.
we will announce it when they get back in the fall. He will contact us and let us know when we're going to start that up again. And we will need volunteers for those nights. And then May
I have a
27th.
question. Okay, the Delta, they had that 12-inch knob that needed work.
Yeah,
Or do we have? an
I have not heard
opportunity?
anything, and I'm sure that it'll be next year, because I'm sure that no one's gonna do anything during the summer. I can email Yatsik and see if he wants to work on it. We can do that. Okay. And then May 27th, couple weeks, we have astronomy in the park, and like I said, we need everybody out there. We had about 100 something people out there on last astronomy in the park. So we would assume that during the summer months that we're gonna have more, so we're gonna need scopes out there. And actually that is becoming, has been a slight problem in the last few months, is we've had a lot of requests for public events with the schools starting to come back and so forth. But basically we have Eric and Bill doing most of the workload. So we're gonna need more telescopes to help out at these things, or we're just gonna have to start telling them that we can't get volunteers to do these things. So I'm gonna need everybody out there when I send out the invites or the asks. I need you to get back to me as soon as possible with whether you can make it or not. So I can get back to the people that are asking for telescopes and let them know yay or nay, because I can't agree to do it and then have only Eric and Bill being available. I've been out on a couple of them because my mom had a stroke about a month ago, and so I'm her primary caregiver. So there's a lot of evenings I just can't go out and do this. So, all right, anything else? That's it for announcements. Any other club business? Is it the
Here's the agenda by
Yeah.
Tim here.
And we thank Bill for bringing the cookies, and we thank Christy for bringing more extra stuff. And we thank Eric for making this all possible. There's underneath that burgundy shirt, it's a big one uni with the red, with the big red S on it. He is Superman. All right. And anything else coming up? We have anything else?
So you checked underneath his shirts.
I saw him changing in a really big phone booth.
Oh, we agreed I can stop recording?
Yep, we can stop recording, I think.